Hey everybody, welcome back to Calc 3 Online. So the plan for today is to do some review related to vector valued functions that we've been studying lately. So you get the quiz coming up, and I just kind of want to do a few problems that kind of from each whole section that we've covered recently. So the first section that we talked about was looking at these quadratic and hyperbolic surfaces, and this is something that doesn't really work super well without you being in class, but I was going to have you, if you were in person with me, I would have you try to think about what these different equations would look like, and then I could keep these things hidden, and then I could show it to you later. But I think it's still good to just talk about why, like, this equation gets you this, and this gets you this, and so on. I mean, planes, I guess, are pretty straightforward. As soon as you introduce squared terms, then you start getting, quadratic or hyperbolic things. But if you don't, you just have basically an infinite, sheet in 3D space. And not that, I really will require it too much, but you can graph planes pretty easily. If you just, you can basically just get intercepts really quickly. So if you put in a 0 here and a 0 here, 4 times 1 is 4. So that means that the x-intercept is 1. Then you could do a 0 here and a 0 here. And then that means that the y-intercept is -4. So let's just say 1, 2, 3, 4. So basically you can do this, and then you can kind of, so we should do z real quick is 2, 1, 2. And then basically the plane is just defined by those things right there. And I mean, it goes forever, but it's kind of hard for me to draw. But that would be the plane. Basically, it goes through those points, if you can kind of visualize that. But definitely no squared terms, you get a plane. Something like this, this is got really just one squared term. I'm actually going to erase this. Want some room. So really what I want to make sure you know is kind of just the fundamental differences between the shapes. And if you get one negative term, right, and then, the rest of these are positively squared terms, then you're going to get this cone structure. And if you have two negative terms, like I have here, right, then, you could divide by, 4 if you want. It might make it a little nicer just because there's a lot of 4s there. But if you divide by 4, you'll get this, right? And the thing that's weird, so this is that thing called, so these guys are called the hyperboloids in 2 sheets, just 2 parts. And then this one is the hyperboloid in 1 sheet. And it's kind of a bad picture, but in this hyperboloid here, it would be a circular hyperboloid. So I talked about one in class that was an elliptical hyperboloid. Basically, if you just divided one of these by a different number, then the y or the z, instead of 1s for both of them, then you would get ellipse in that direction, basically, and not a circle. And I also wanted to say again, so the thing that's kind of weird, and the reason you're getting this gap, is if you, say, let y equal 0, then you get -x squared minus z squared equals 1. And this thing is not solvable with real numbers, right? So there actually is something going on in the complex plane right here, but we're not going to worry about that right now. So, but basically you can see that there's just certain values here that are basically going to make it undefined. This is the y-axis, right? And it's -2 and 2 because as soon as you get this to be a 1, then you can solve it, right? Because you could do, if you have negative x squared plus 2 squared, let's say, then this is really a 1 and that's a 1. And then you could have negative x squared minus z squared equals 0 with x equaling z equaling 0. And so that's like the very first time that it makes sense. And that'd be the same for negative 2. But then you can plug in all these other y values and stuff. But you can get these hyperboloids in one sheet or in 2 sheets. All right, so this is probably one of the more kind of useful things that we kind of end up, I feel like we do with vector valued functions down the line. So there's a lot of problems where we need to see like the curve of intersection between two things. A lot of times it's with like, I took like a celestial mechanics class in college, and we did a lot of this where we would be given some sort of surfaces, and then we would basically represent it with vector valued functions. But you have to figure out some sort of parametric equations, which when you plug them in make this expression true, and then you can use those x and y's to get z here. So this is basically just a circle with a radius of 4. So if you just let x equal 4 cos t and y equal 4 sine t, you can see you get, if you plug it in, right, you're going to get 4 squared 16 cosine squared, 16 sine squared, and then you take your 16 out, and you get cosine squared plus sine squared, which is going to go to 1, and so it really does equal like 16. And so then you can take x and plug it in here to get what z needs to be. So in here you would have 4 cos t plus the z needs to be 5. So z is just 5 minus 4 cos t. So this is basically the curve of intersection. You would get 4 cos t in x, 4 sine t in y, and then 5 minus 4 cos t in z. And this is one of those things, if you just go to Math 3D, you can actually go and plug this in like I did in class, and you could plug this in, and you could really see that these surfaces where they intersect is represented by this vector valued function. Another one too that sometimes kind of gets people, if you have things like, say I have just a quadratic, like y equals x squared over 2 or something. Sometimes like these ones, if you want to like define this with parametric, it's almost like so simple it's hard kind of thing. You can literally just do something and you can say let like x be t, and then y just has to be t squared over 2. That actually will do it. If you go and like plug, we know that it just looks like a quadratic, right? If you do these parametric in like in a 2D plane, you will literally see the exact same quadratic. It'll just look like, something like that in x and y. But you can literally do that. You can just let like one variable be like t, and then the other one it becomes the function with t now. That showed up a few times in the homework, and that's kind of another important one to know. So another thing that you will have to do on the problem set is finding curvature for different vector valued functions. If I was given this one, the fact that it's just a 2D curve, so this is actually just an ellipse because 5 is not equal to 4, I would basically use the kind of 2D curvature formula. So the one that's just magnitude of the unit tangent, the derivative of the unit tangent, over magnitude of r prime. And if it's at that point, you can really just plug in, honestly, you could just get this all in terms of t, or you can like plug it in as you go. So let's just do it. So r prime is 5 or minus 5 cos, minus 5 sine t for cos t. And then if you think about the definition of the unit tangent vector, the unit tangent vector is r prime over the magnitude of r prime. So we will need the magnitude of r prime here. So the magnitude of r prime is just the square root of each component squared, right? So we get 25 sine squared t plus 16 cosine squared t. So this thing is kind of annoying because you can't do like a trick that we've seen a lot where you factor it out and you get a sine squared plus cosine squared to cancel. So you actually can do a kind of a +1 -1 trick where what I'm going to do is I'm going to add 16 sine squared t, because then that'll be nice with the 16 cosine squared, but since I added something, I have to subtract it in order to keep the equation the same. So this part is really just like adding a 1. And then I can take these, right, and I could factor out a 16 and use that trig identity. And then this is kind of nice because now this will combine with this, and you get 25 minus 16 of them. So you get, that's 9 sine squared t plus 16 after you use the trig identity. So it's just to make this thing look a little bit nicer than this. So this is getting kind of messy kind of quick, but basically the unit tangent vector is just defined as 1 over the square root of 9 sine squared t plus 16. That's my magnitude of the r prime vector, times the vector -5 sine t for cos t. So now you have to do the derivative of this. But this thing can actually be simplified because we can take this and just evaluate it at like t equal to pi over 3, right? And if we do that, we're going to get the sine of pi over 3 is root 3 over 2. So if you square it and plug it in there, you're going to get basically square root of 9 times, come on, pen, 3 over 4 plus 16, which is like about 4.77 if you use a calculator. So really we can take this thing and just make it, where was it? Yeah, I need to get rid of that too. So we can put 1 over 4.77. And now we can just do t prime, right? And we can just take and basically pull those scalars out in front. So we have like -5 over 4.77 times the derivative, the derivative of sine, which is cosine. And then 4 over 4.77, derivative of cosine is negative sine. And that's like a much quicker way to do it, basically. And then you will need to evaluate that thing. Well, you got to get its magnitude too. So we are running out of room kind of quickly here. Magnitude of t prime will be, so again, this is just a situation where I would use a calculator. You get something like about 1.1 cosine squared t, and then if you square the second component, you get some about 0.7 sine squared. And really at this point, I would just go and plug in pi over 3 for t. And if you do that, and again, I'd probably just use a calculator. So if you plug in pi over 3, you should get something that's about, it's basically about 0.9. So I think we have all the parts we need now. So we can just go, we have k of t is equal to the magnitude of t prime, which is like 0.9, over the magnitude of r prime, which is like that 4.77 number. And if you do that on a calculator, you get about 0.18. We're going to say 8, something like that. It's a lot of decimals. That don't mean a ton, to be totally fair, but the idea of just finding curvature, I kind of want you to see. So there's a lot to say about curvature, and I could talk about the fact that this number is positive means something versus negative, but there's other courses where you'll learn more about that stuff. But this is basically just a measurement of how much this ellipse is curving at pi over 3. So another really important part of vector valued functions is understanding them in terms of physical meaning, like position, velocity, and acceleration. And it's important that you can basically take, something that is position, velocity, or acceleration, and give you any of those, and that how to use derivatives to go up the chain, and then how to use integrals to basically go. I don't really have room, but how to do integrals to go down the chain. And so I could give you a question like this, where I give you the acceleration of an object is given as 0 in the I, t in the j, and t in the k. And then I tell you the velocity at time t is a certain vector, and the position of the object at times t is a certain vector. And then I want you to find the object's position at any time. So basically I want to know what is r of t, for all t. So it's just an integral problem. So I'm going to integrate a of t to get v of t, and I would get t squared over 2 there, t squared over 2 there, and I would get a constant vector. And we know that v of 1 has to equal 0, 5, 0. Right now, if you go and plug in 1 up above, we're getting 0, 1/2, 1/2, right? So that means that, I should label this thing. That means that the c vector definitely has 0 in the I component, and then it's 4.5 in the j, and then it's minus 1/2 in the k component. So then you can actually get a full-fledged velocity vector. So your velocity vector would just look like 0, t squared over 2 plus 4.5. Right? I'm just adding c to the c vector to v. And then k would look like t squared over 2 minus 1/2. So then basically just restarts, I guess. So r of t, we're going to integrate v of t. And if we integrate 0, we're going to get 0. We're going to get t cubed over 6 plus 4.5t. And then we'll get t cubed over 6 minus 1/2 t. And then again, we'll have I'm going to call it C2. I'm actually going to go back and call that one C1. So I'll call that one C1. And then if you do the same kind of things as before to figure out C2, right, we know when we plug in 1 right now, what we're getting is 0, 1, 6 plus 4.5, 1, 6 minus 1/2, and this thing needs to equal the 0 vector. It needs to equal 0, 0, 0. So that means that C2 equals 0, negative 14 thirds and 1/3. And you can check it. I'm just not going to go through it because I basically do it for the purple one here, but it works the same way. I'm just, I can see I don't need to add anything to this to get to here, but this is 14 thirds, so C2 must have a minus 14 thirds here. Basically, it cancels it out to get me 0. And it just works like that. So then the final, like R of t vector would just look like 0, 1/6 t cubed plus 4.5t minus 14 thirds for j, and then t cubed over 6 minus a half of t plus a third for k. All right, so another thing that I want to make sure you know at this point is arc length for vector valued functions, and this problem is just a weird arc length problem, and I think it's kind of actually interesting too once you get the answer to this problem. So basically we're going to kind of think of DNA molecule as just like a one-dimensional space curve, and the helix, basically if you think of cutting it, it's going to look kind of like a circle, and in like, let's say x and y, and the radius of each helix is 10 angstroms. 1 angstrom is 10 to the negative 8 centimeters. You use this for like measuring super small stuff. So I actually was like a molecular bio major when I first started undergrad, and you work with these things all the time if you study that stuff. But and it says that the helix rises 34 angstroms for each complete turn. So that actually should be enough to get parametric equations for a double helix. So basically we're finding, this is really just like one of, these strands here. It's not like we're finding both of them or something. But if you like cut it this way and you kind of look at it, like basically if you like project it down into like, let's say x and y, then it has to look like a circle. And the circle just has a radius of 10, so we would do 10 cos t, 10 sine t, and then it says that the helix rises 34 angstroms for each turn. So that means that the z component would look like 34 angstroms per 2 pi if we're like in radians, right? And then t to scale it and bring it like up and I guess down too. But that actually would define a spiral, that goes like up and up and up and up and up and up. And the radius of this spiral, like from here out, that distance is the 10. And then the length of time to do one complete cycle here is defined by the 34 angstroms per 2 pi. So this would do it. This would describe, we have like a vector valued function to work with then. So if we want to do arc length, basically, I don't know why there's arrows here. I'm going to cover that up, then I can write over it. So I want to, so the limits of integration for this problem, we want to know how long each helix is, and if they are 2.9 times 10 to the 8th complete turns, then we can just go and take an integral from like 0 to 2.9 times 10 to the 8th complete turns, and complete terms in math classes are 2 pi, right? So this is basically my integral, which let me make this a little bit better. And inside, if I just use like the arc length formula, we have you just take the bounded magnitude of r prime vector dt, and so in this case we go 0, 2.9 times 10 to the 8th times 2 pi, and then we would have square root of 10 cosine t squared plus 10 sine t squared plus 34 over 2 pi squared, and dt. And, oh, wait, I dropped a t in here too. And this is not an integral like I would recommend you try to do by hand. It's super messy with crazy numbers. And if you go and just like plug it in, your calculators can actually do it too. I did it online, but it's about 2.07 times 10 to the 10th, okay? And so this is in angstroms, okay, which we do with this weird little, it's like an A, it's like a circle on top. That's like the unit. So what I want to show you is how many meters that is, which is the weird part to me. So we have this 2.07 times 10 to the 10th, right? And that's in angstroms. And then we know that there are, for like one angstrom, there is 10 to the negative 8 centimeters. And we know that for 100 centimeters, there's 1 meter. And so if you do the little, like, what do they call this, dimensional analysis stuff, and you cancel and multiply all this across, this is basically about 2.07 meters. So that is how long, and these are actual numbers. This is like the correct way to do this problem. That is how long the length of each helix of DNA is, which is crazy that it's that long and it's all like wound up inside of your body like that. I always thought that was a crazy problem when I first saw that one. But yeah, that is literally how long like one of these strands is inside. It's just like bundled up, and if you stretched it out, it would literally be 2.07 meters, which is crazy. That was there in case I needed more space, which I don't. I thought this was kind of cool too. So these are just like other weird facts about DNA, I guess, is what I have here. So I was really into this stuff when I was at the end of high school, and I was focusing on molecular bio in particular, but I really wanted to be like pre-med. But these are just the kind of weird things that I always thought was really cool with biology. So I'll let you just pause it and read it. I don't need to read them to you, but I think these are kind of cool facts that you should read.